Welcome to Everyday Mathematics. Here at Everyday Mathematics, as we always say, we do enjoy solving the harder problems, but above all, we also do see and appreciate the beauty in the simpler problems. So today, our focus is on the MIT 2024 Integration B Finals, problem number 5. This is a very interesting problem. I really did enjoy going through it. But before going on to the question, I'd like to thank our subscribers. Thank you so much for your amazing support. That's because of your support that we come here time and again to share with you some of the amazing solutions that we do come up with. For our first-time visitors, we at Everyday Mathematics, what we do is we go about looking for problems that may seem challenging. We try to solve them, and we come back here and share with you the solutions. So we do really encourage you to consider subscribing to our channel. For our repeating visitors, we would like to encourage you to subscribe if you're not subscribed. But other than that, welcome again. Going into today's problem, it's the integral from x equals to 0 to x equals to 1 of the maximum values choosing from the integer n greater than 0 such that the expression 1 over 2 to the power n in bracket floor function 2 to the power n x minus floor function of 2 to the power n x minus a quarter is maximum. So what this problem is asking us is that at any point of x, given the multiple options that we have, we should pick an absolute maximum of the many options that are available, which is a very interesting problem. What I like to do first of all is to explain what a floor function is. A floor function is a function that extracts the integer lower than any real number that you give it to. So for example, if we're looking at floor function of x, that is equals to integer k when x lies between when x is greater or equal to k or less than k plus 1. As soon as x is equal to k plus 1, this value shifts to k plus 1, and so on. Then the floor function of 2x is equals to k when 2x is between the integers k and k plus 1. As soon as 2x becomes k plus 1, this becomes k plus 1. But so long as 2x is greater or equal to k and less than k plus 1, then the floor function of 2x is equals to k. So in that event, that means that x should be greater or equal to k over 2 and less than k plus 1 over 2. So if we were to plot this, it means that when x is between 0 and 1, the floor function of x is 0. And when it hits 1, it changes to 1. And it stays there until x is 2. And when it becomes 2, it transitions quickly to 2. And that is what a floor function does. Now, if you to consider the floor function of 2x, so because 2x becomes 1 at a half, that means that from 0 to a half, we have 0 as the floor function of x. And as soon as we reach half, it becomes 1. And it becomes 1 up to 1. And that when x equals to 1, we have 2 times x, or 2 times 1 being equal to 2. And so it transitions to 2. And then it stays at 2 until we get until 1 under 1.5. And then at x equals 1.5, it transitions to 3, and so on. And that also would happen if we have a floor function of 4x. At a quarter is where it becomes 1, and then it stays there up till a half, and at a half, half times 4, we get 2. It stays at 2 until 3/4, and it transitions to 3, and then at 1, it becomes 4, and so on. So that is what a floor function does. Now, that's what I just described. Now, for our problem, we have, let's begin by looking at the floor function of 2 to the power n x minus the floor function of 2 to the power n x minus a quarter. So when n equals to 0, what happens is that we have x, floor function of x, minus the floor function of x minus quarter. So if we have our graph like this, it means that from 0 to 1, 0, and then from 1 to 2, it becomes 1, and then from 2 to 3, it becomes 2. Now, x, floor function of x minus a quarter. So first of all, from 0 to a quarter, from 0 to a quarter, this expression is negative a quarter. So the integer lower than negative a quarter is negative 1. As soon as we hit a quarter, this expression becomes 0. And then from there onwards, everything is 0 until 1 and a quarter. That's where now it transitions to 1. And it continues to be 1 until we are at 2 and a quarter. That's where now it transitions to 2, and so on. So you see that we do have a lag here, we do have a lag here, and we do have a lag here. Now the difference between the floor function of x and the floor function of x minus a quarter at this point, from 0 to a quarter, will be 1. And then from 1 and 1 and a quarter, the difference will be 1. Otherwise, all the other places will have 0. And then between 2 and 2 and a quarter, the difference will also be 1. So we are only having these 1 intervals from 0 to a quarter, and from 1 and a quarter, from 2 and 2 and a quarter. So this only happens when the function is transitioning to the next integer. So because of the lag that exists between these two functions, you have a difference of 1 for the duration where the two functions are not equal. So for n equals to 2, n equals to 1, sorry, we have the floor function of 2x minus the floor function of 2x minus a quarter. So what that means is that for the floor function of 2x, from 0 to a half, it's 0. From a half to 1, it's 1. From 1 to 1 and a half is 2. And then from 1 and a half to 2 is 3. And then for the floor function of 2x minus a quarter, again, we have that lag comes in, but the transition now happens at x equals to 8, because at x equals to 8 is when now 2x becomes a quarter, and this becomes 0. So the lag happens for only 1 over 8. And so you see it happens at the transition, that's at 0, and then at a half, and then at 1 and 1 and a half. So those transitions where the function 2x is changing, its value is where you have this lag. And therefore, at 0 to 1 over 8, you have this difference being 1 for the duration of 8. And then from a half to a half plus an eighth, you have another difference over 8. And then from 1 to 1 plus an eighth is where you have the difference over 8, and so on and so on. So as you see here, what happens is when you increase the value of n from 0 upwards, 1, the number of these difference points increases, but also the width also decreases. But the difference remains to be 1. So we're having these rectangles with a width of changing from a quarter when n is equal to 0. It changes to an eighth when n is equal to 1. When n equals to 2, it changes to 1 over 16. But the height remains to be 1. So that is what this expression is all about. Now, for our problem, choosing the maximum, we have to do a little bit more. So looking at n equals to 0, we saw that in that between 0 and 1, when x equals to 0 to x equals to 1, we had only the transition or the lag existing for a quarter, and that's when that difference was 1. In other regions, it was 0. When n was equals to 1, we saw that the lag existed at 2 points between x equals 0 and 1. That was at 0, x equals to 0. And then when x equals to a quarter, and so we have these rectangles, these two locations. When n equals to 2, we expect it to be at 0, but the width being now 1 over 16 will be at 0, at a quarter, at a half, and at 3/4. When n equals to 3, we expect to have the lag existing at x equals to 0, at x equals to an eighth, at x equals to 2/8, x equals to 3/8, x equals to 4/8, which is a half, 5/8, 6/8, 7/8, right? And so that is how the progression goes. And then when n is equals to 4, we expect it to be the transition to be at x equals to 1 over 16, 2 over 16, 3 over 16, 4 over 16, and so on. So the next thing now is to now consider this factor of 1 over 2n, right? To the power n. So what this means is that as n increases, because we have this factor, the entire value here decreases, even if the difference is 1. So our choice should be that as long as there is for whatever region from x equals to 0 to 1, the lower the integer n, the higher or the more maximum the value is. So it makes more sense because from n is equals to 0, the factor is 1 over to the power 0, which is 1. Here we are multiplying by 1 over to the power 1, which is a half. Here we are multiplying by a quarter. Here we're multiplying by 8th, and here we're multiplying by 16th. So definitely in this region where we have a difference, this is the maximum. And because we've already chosen here, in the next subregion, we will ignore this and consider here, because here between a half and 5 over 8, because there is no value when n equals to 0, this becomes the maximum. And going on, when n equals to 2, because we've already chosen this to be our maximum value, we will only go and say, okay, this will be maximum in this region because there's no other candidate here. And we cannot choose this because we've already chosen this region or this to be our maximum. But here, because there's no prior value here, we will choose this. The same will happen here. We cannot choose this, we cannot choose this, we cannot choose this, but we can choose this because this is the only candidate with nothing in the lower values of n. We'll choose this, we won't choose this, we will choose this, we will choose this. So there are three, there are three candidates there. And then with here, we won't choose anything here. We will choose this. We will choose this. We will choose, we won't choose this. We won't choose this. We won't choose this. We'll choose this. We will not choose, we probably will choose this and we'll choose this. So that's how you go about choosing the regions that give you the maximum value for that specific interval. So essentially what happens is for n equals to 0, this is what we'll choose, what is in red here. For n equals to 1, we'll choose this. For n equals to 2, we only choose this and this. For n equals to 3, we choose this and this and this. So we have 3 points that we'll choose. And then for n equals to 4, we will choose this, this, and this, and this, and this. So we'll choose 5 rectangles. And so as we can summarize, for n equals to 0, the choice is 1 rectangle. For n equals to 1, there's only 1 rectangle. For n equals to 2, we're choosing 2 rectangles. For n equals to 3, we are choosing 3 rectangles. For n is equals to 4, we're choosing 5 rectangles. Now, there's definitely a series that, or a pattern we're seeing here. If you see here, this first one is the same as 0 plus 1, we get this. And this here is the same as this 1 plus this 1. Okay? This 3 here is the same as 1 plus 2 goes to 3. And this 5 here is the same as 2 plus 3 being equal to 5. And in succeeding ends, we'll have to follow that sequence. And this is what we call the Fibonacci sequence. It is a very famous sequence in mathematics and computer science. So knowing that, our integral therefore is, what we'll do is it's for n equals to 1, we know that constant is 1 over 2 to the power 0. And then the rectangle is of width a quarter, and the height is 1. And then there's only one rectangle. And then for n equals to 1, the constant is 1 over 2 to the power 1. And then the width of the rectangle is 1 over 8 times 1. And then there is only one rectangle to be considered. When n is equals to 2, 1 over 2 to the power 2, the width of the rectangle is a 16th. And then the height is 1. And there are 2 rectangles to be considered. When n equals to 3 is 1 over 2 to the power 3, the width of the rectangle is 1 over 32, and then the height is 1, and then there are 3 rectangles to be considered. And when n equals to 4 is 1 over 2 to the power 4 as the constant, the width of the rectangle is 1 over 64 times half, which is the height, and then there are 5 rectangles, and we continue so on and so on and so on. So what this results is 1 over 2 to the power 0 is 1 over 1, which is 1. But now we're left with the quarter here. 1 over 2 times 1 over 8 is 1 over 16. 1 over 4 times 1 over 16 is 1. It's times 2 is 2 over 64. 1 over 8 times 32 is 256. Times 3 is 3 over 256. 1 over 16 times 1 over 64 is 1 over 1024 times 5 is 5 over 1024. So this is the same as 1 over 4 to the power 1, 1 over 4 to the power 2, 1 over 2 to the power 4 to the power 3, 2 over 4 to the power 3, 3 over 4 to the power 4, 5 over 4 to the power 5. And then this constant here, as we've said, the Fibonacci elements, so members of the Fibonacci sequence. So this is F1. We've omitted F0, so we have F1, we have F2, we have F3, F4, F5. For F0 is 0. So the important thing to know is that the Fibonacci sequence, before we go there, we can just quickly express this as the summation from k equals to 1 of the kth value of the Fibonacci sequence over 4 to the power k. The Fibonacci element, or the kth element, can be expressed using this golden ratio. But I mean, you can go and do some research. The kth value is 1 plus root 5 to the power k minus 1 minus root 5 to the power k over to the power k times fifth. So we can simplify to say that this is 1 plus root 5 over 2 to the power k minus 1 minus root 5 over 2 to the power k over root 5. So we can put these in place of fk so that our integral is now the summation from k equals to 1 to infinity, or 1 plus root 5 over 2 to the power k minus 1 minus root 5 over 2 to the power k over root 5 over 4 to the power k. Now, I can pull this 4 into this expression and here, and then pull this outside here. Okay, that constant. So we do have a 1 over root 5, and we have 1 over 2. So let's pull this 4 in. So we have 1 plus root 5 over 8 minus 1 minus to the power k minus 1 minus root 5 over 8 to the power k. So this is a geometric series. The initial value will be this to the power 1. So we have 1 over root 5 with the initial value being 1 plus root 5 over 8. And then the denominator is 1 minus the common ratio, which is 1 plus root 5 over 8. The same thing for the second one. So as we can see, we can now get the common denominator here, and this becomes 8 minus 1 minus root 5. And the 8 cancel out, so we have 1 plus root 5 over 7 minus root 5 minus 1 minus root 5 over 7 plus root 5. And then when you multiply the denominators, so because this is the product of the difference and the sum, we have 7 squared minus root 5 squared, which is 5. And then this divided by this, the product divided by this times this is just 1 plus root 5 times 7 plus root 5 minus 1 root 5 times 7 minus root 5. So 1 times 1 plus root 5 is 7 plus 5. And then 5 times 7 plus root 5 is 7 root 5 plus 5 times 5, which is 5. The same thing happens here. So we have to, because this is plus, so we are adding 5 here. So as you can see, this cancels with this, and then this cancels with this. Now we are left with 8 root 5 minus minus, which is now plus another 8 root 5. So we do have 16 root 5 over 44, because 7 squared is 49 minus 5. And then since this cancels with this, and then 16 divided by 44 by 4 goes 4. And then by 4 becomes 11. So our final answer is 4 by 11. And this is the answer to this problem. So it's certainly a very interesting problem. If you do have any questions, please leave us a comment or any feedback, or if you have any alternative solution, we welcome your suggestions. Here at Everyday Mathematics, we do enjoy interacting mathematically with you, and we hope through the many interactions we have, we can both grow. So if you haven't subscribed to our channel, please consider subscribing to our channel. We do love mathematics here at Everyday Mathematics, and we hope to have a dialogue along those lines. Until next time, ta-da.